Ah, there we go. Okay, mic sounds good. Can everyone hear me in the back, front, everywhere? Okay, great. So thanks for joining us this afternoon. This is the IoT Security from Manufacturing to Maintenance talk. My name is Tim Madison. I'm the Global Tech Lead for IoT Partners at AWS. I focus as a solutions architect that works on IoT solutions across a broad range of partners, and I do a lot of technical deep dives. Last year we did a presentation about AWS IoT services and how those services are secure, and the feedback that we got from customers that they want to know more than just how our services are secure, but how they can build secure hardware themselves, how they can build secure software. So I'm joined here today by Xavier from Microchip. I'm going to go through the manufacturing and maintenance side on the cloud aspect of it, and then Xavier is going to talk about some of the components that Microchip has to enable customers to build secure solutions on AWS. But first, in the past 2 years of going through discussions with customers, we've heard a lot of myths about IoT security, and I just want to dispel some of those first. If you're in a position where you need to justify embedding security into your solution, there's cost involved. There's a lot of things that you need to convey to somebody that they may come back to you with one of these myths, and hopefully this can help you in that discussion. So the first myth is my solution doesn't need security. And the most common reason for this is people say, I'm building a temperature sensor. It doesn't matter if the temperature sensor is impersonated by somebody else. But the first question you have to ask yourself about every IoT solution is, where does that data go? Temperature data might seem like low value data, but somebody downstream is taking that data and just trusting it. If they can fake that data, you can end up with some serious problems. So what decisions are actually made with that data? Do I see that a temperature sensor is saying it's 0 degrees outside, so I shut an entire building down? Do I turn on a heater? Do I turn on a chiller? Do I take a piece of equipment out of service? Do I initiate an automatic service call to somebody that costs us a lot of money? Even if it's just a simple piece of data, it needs to be secure. It needs to be trustworthy for all the downstream applications. And you may not even know what those downstream applications are, so it's just another reason why you have to take it seriously from the start. Initially, you might know exactly where your data goes, but as these services allow you to decouple things, somebody else down the road is going to depend on that data, and if it's not trustworthy, it's not valuable. It's actually a detriment to your projects. Are these decisions important to your business? Some people say, well, I know where the data is going to go, and we're not really doing anything exciting with it right now, so I'm not going to incorporate security. And what I would say to you is, if you can't really find that there's business value in the solution that you're building, you need to ask yourself a different question, and the question is, should you actually build it in the first place? So any solution that's valuable needs to have security in it, and all these IoT solutions are like that. The second one is a little bit harder to dispel, but people say with physical access, all bets are off. And we've seen a lot of compromises of consumer hardware. People can take it apart. They can pull off the firmware. They can extract the keys. They can do all kinds of things to just know exactly how the device works and impersonate that device. Now, years ago, that was the state of the art. Everything was unencrypted flash. Everything was in main memory. But hardware security has changed significantly in IoT. And you need to be aware of those changes to understand all of the different technology that's out there. And even some of the equipment you're using today may have security features that you don't know about. A lot of devices out there, even if they're minimal devices, they might support secure flash, secure boot, all kinds of different technology that would enable you to build a secure solution, but you may not have it turned on. So we'll talk about that. And one piece of advice that I would love to give everyone is just, when you take a device to production, disable the debug interfaces. This is a security and a stability issue. I personally worked on a project where we didn't disable the debug interfaces because we were kind of in a pilot situation, but that debug interface provides a root console to Linux on the device, and if anybody can get access to it, they can get into the device. Even if you disable that, what we ran into was the bootloader, when a device rebooted and had a noisy power supply, it thought that somebody pressed a key and it just sat in the bootloader forever. So the device would reboot and just never come back to life. So it's more than just security, it's stability of your application. Debug interfaces aren't just JTAGs. Sometimes they're UARTs that are just serial ports where you can configure the device, control the device. You need all of that stuff turned off when your device goes to production. And you should have a test fleet also that has those features disabled, so you can see how it operates in the field, or how it's going to operate in the field before you ship it. So don't use physical access. People are going to have my hardware in their hand as an excuse to not build security into your solution. And then the final myth is security at this level is too expensive. We're going to talk today about secure elements. We're going to talk about how secure elements protect your private keys. And people think immediately, well, tamper-proof hardware or tamper-resistant hardware, all of this stuff has got to be really expensive. But the fact of the matter is that the typical BOM cost for somebody doing a moderate production run is about 50 cents to incorporate this piece of equipment. And ask yourself this, even if 50 cents seems like a lot of money for your bill of materials cost, how much is it going to cost you to fix that device in the field if something goes wrong? If somebody says, well, we accidentally deployed it with shared keys and we need to go out and fix everything, rolling a truck once costs hundreds of dollars probably. If you need to replace the whole fleet, that's going to cost you a fortune. And if there's a compromise, on top of that, how much does it cost to fix the customer perception of your product? If people see a news article that says product X was compromised, customer data leaked, it's not likely that it's going to be easy for you to go into meetings and say, oh, you can trust us now, we fixed the problem. You need to do it from the start. So what are we actually protecting against? I want to give you a couple of threats to consider, some that might not seem like threats, but we'll get into why they are. The three that I chose are the third-party manufacturers. These are the companies that are building your device for you and kind of have the keys to the kingdom. They have your design, they have your firmware, they have all of this stuff. What can they do and what are the threats that you should worry about there? Private facilities, those are essentially facilities where you own the building, all the employees that work there are your employees, and you feel like you should be able to trust the people in the building, and you're kind of using physical security as your security layer. And then there's the end user. This is when you build a consumer device, then you ship it, and somebody can just take it home, unbox it, and do whatever they want. Pull the chips off, start pulling layers off of the chips. They can do anything they want. What's the risk there? So third-party manufacturers, again, they've got your designs, they've got your firmware potentially. What can they do? The primary risk that you should look out here is counterfeit goods. If somebody can just make counterfeit goods and you don't have a strong traceable identity for the device, you don't know which ones you've actually paid to create, then they're going to sell it to somebody else and you're not going to get paid for it. But an important secondary risk that people miss sometimes is that there's a cost of supporting those goods. We're here at the AWS reInvent conference. These devices are going to be connected to the cloud. You've probably baked in how much it costs to run this device for some number of years into the price of selling it. If somebody buys a counterfeit good and then you don't get any of that money and you can't identify that it's counterfeit and you have to pay to operate it, then you have two losses on your hands there. So private facilities, what's the primary risk there? If you're using simple physical access as your only mechanism to protect your devices, anybody who can get access to your building at any time can just take the device, take it apart, and then impersonate it. Maybe they can only impersonate it from inside the facility, maybe they can impersonate it from everywhere, but you really shouldn't depend on just blocking physical access as your way to secure your device, because anybody can just take it apart. And then the other risk is that maybe you have devices that are communicating to building automation systems or other systems that your employees don't have direct access to, but the device has credentials baked into it to give them access to it. If one of your employees or anybody pulls those credentials off, now they can elevate their access and get access to some system they didn't have before. So there's no need to embed those credentials in a way that they can be pulled off. So you shouldn't do it because it'll put you at risk for people escalating their privileges. And then the end user. So in the example here, we'll consider something like pay TV, video rental service. The primary risk is that customers will steal services from you. If somebody can just, again, take apart your device, extract the keys, and rent a movie for free, they're going to do it, and you're going to lose that revenue. But just like in the other cases, you're now liable for that content to other third parties. So you've got the loss of the initial revenue, and you have the loss of having that liability in your book to pay for that rental that nobody paid for. So what do we do about all this? We know that we need security. We know that there's a whole bunch of risks out there. There's more risks than I've outlined here. So in the manufacturing phase, we need to take this seriously, and we need to have some kind of hardware-based solution to it. So today what we're going to talk about are secure elements. And secure elements, in my mind, are kind of the simplest way to get security into your product. They're usually devices that have an I2C interface, and they protect your private keys from exfiltration. They have, they're designed so that the private key is generated inside the chip, and then you can't pull that private key out for any reason. And the device will do the cryptographic operations you need to do with the private key inside the device. And it provides this well-defined static interface. It gives you a couple of simple operations you can do with the key. And what are those operations? Simply, you could verify a signature. It's got a crypto engine that you can use to accelerate that. You can generate a session key, which on some microcontrollers might be really expensive. You may have a really bad random number generator, but secure elements have true random number generators in them, so you can use that to generate your keys. And they can generate a signature with the private key. And we see that devices that you see in the field that have very low compute power, with a secure element, not only do you get the protection of your key, but you get a faster response time because the chip is accelerated to do these crypto operations. And you get much less power consumption. We had an example of a device that took about 15 seconds to negotiate a TLS 1.2 connection, and with a secure element it took under 100 milliseconds. So you're saving 15 seconds of the device being online doing this operation while still protecting it for the cost of approximately 50 cents. So how does it work in the manufacturing process? So there's you want to get your device manufactured, so you contact a secure element manufacturer, and you give them a CA that they're going to use to sign the device certificates. Now, typically, you would provide this to them in some secure fashion, put it on a hardware security module, and then they're going to manufacture a bunch of secure elements, and they're going to provide you information about how many devices they manufacture, potentially the serial number of those devices, but give you some indication of, we made 10,000 of these devices, and you're going to use that information later to make sure that the certificate authority you used with them doesn't get reused somewhere else. You know exactly how many devices are coming out. So then your secure elements get sent to the third-party manufacturer, and now that third-party manufacturer doesn't have the ability to look at your credentials. They just have this device that they can, when they have it in their hands, they can ask it to perform an operation, and that's it. As soon as they've put it in the device and shipped it off to you, they have no access to this information anymore. And they turn those into finished devices, and then you send them out to distributors. So how does the secure element itself actually get provisioned, though? The secure element is going to be on the manufacturing line at the secure element manufacturer. It's going to fire up its random number generator, and it's going to generate a private key. The secure element manufacturer isn't going to generate these private keys and inject them into the hardware. They're going to generate it on the device itself, so you can have proof that it's never left the device. The device is going to generate a certificate signing request, which is then going to get signed by that HSM that has your certificate authority on it that you've sent to the secure element manufacturer. And this all happens in the manufacturing line. Certificate's going to come out of that, and then the certificate's going to get stored back onto the device. And the certificate is public information, so there's no concerns about that getting shared with anybody else. Then how do you onboard the device? In the case of AWS IoT, you've got AWS IoT in the middle. You're going to provide a CA verification. You're going to use the CA HSM before you send it off. And you're going to get a verification certificate that says, I have ownership of the private key of this certificate authority, and you tell that to AWS IoT. And now we know that any device that comes from that certificate authority was manufactured by you. Your devices are going to connect into the service, and then one way that they can be validated is they go through the just-in-time registration process. The device sends its certificate. We then check and see, is this a device that we expect? Is it signed by the certificate authority that you created? And if it is, we'll attach policies to it. We'll do all the configuration that you want in a Lambda function. But if it's not, we can log it and reject it. And again, the secure element data you get back from the manufacturer is very important because that will help you build this Lambda logic that says which devices should I accept and which should I reject. The CA part of it is a very strong identifier of the fact that it's a genuine part, but knowing exactly which devices is an additional step you can take on top of that. So now we've got a device manufactured, but we need some software for it. So how do we make sure that we write software in a secure way? How do we make sure that that process is secure? So we'll talk about a couple of maintenance best practices. The first one is really interesting. I get tons of questions about this. Sign all firmware, even when you're in development and test. Some people say it's not necessary, but we've seen customers in the field, when they turn on code signing and they deploy things to the field, something's different. There's just some kind of different operation of the chip that they haven't tested for and they haven't looked at. So you need to do that in dev and test. Now the keys to sign the firmware in dev and test should be different than the ones you use in production, and developers can have access to the dev and test keys. That's fine, or at least the dev keys, so that they can iterate quickly. But you still need to test that feature as it's turned on, because it does sometimes change the behavior of the chip. And you should separate your development team from your deployment team. Continuous integration is great, continuous deployment is great, but when you're deploying to devices, you want to make sure that a mistake that some developer makes doesn't automatically get propagated down to a giant fleet of devices. So you want to have developers develop their code, be unblocked, not worried that it's going to get pushed out into the field, and then leave it to a deployment team to deploy that. And then you want to do stage rollouts of firmware updates. You're going to update devices in dev and in test, and you're going to have different environments for that, hopefully. And you're always going to want to do a stage rollout. You never want to brick devices. You're probably going to have a dev fleet that's unlocked that people are making changes to often, but you're also going to want to have a dev fleet that's totally locked down so you can see how the device actually operates in the field. And you don't want to brick all those devices at once. If you make a mistake that bricks a device, you don't want to brick those devices that have been securely locked down. And only allow control from the cloud if possible. And I say cloud here, could also be Greengrass, could be a local gateway, could be something else that provides control. But if you have devices talking directly to each other and you end up with a device that's compromised, that device can wreak havoc on other devices without having an intermediary. So that intermediary could just be your broker, could be a Lambda function, something that you have the ability to, as a circuit breaker, just turn it off if something goes wrong. So how do we separate roles when we're doing continuous integration with this development and deployment team? First, we have the developers on the top, and they're going to commit a bunch of code, which is going to go into your CI system. And if the tests fail, it goes back to the devs, they keep developing. But when the tests pass, you take the artifacts, the build, whatever you've got coming out of that CI process, and you're going to drop it in S3. You don't just drop it in any S3 bucket. It's a very specific bucket. It has versioning enabled. It's write only by your continuous integration system. The developers have no access to it whatsoever, and it's read only by the deployment team. You want to make sure that nobody can go in there and tamper with these bits without you noticing. So all of those features need to be turned on. Then your deployment team is going to go into this bucket. They're then going to use KMS or Cloud HSM or some other facility to sign the firmware, hopefully uniquely for each device. And then they're going to do what we talked about, the staged rollout of all the firmware onto your devices. How do we further separate roles? Having a S3 bucket is a nice way to lock down permissions, but if you can, keep everything in separate accounts. Now, production always be in a separate account no matter what. That should be the lowest bar. But when you can, developers, tests, everything should be in a separate account. And even your deployment team should be in a separate account. When you're writing to that S3 bucket, if you're using a cross-account role, you have even more control about being able to say who can access it. Because somebody can't go into the console, get admin access somehow, and then change their permissions and change them back. If it's in a completely separate account that they don't have access to, you can be sure that nobody's tampered with it. And then if you really want to add another step in there, you can move your build from the development environment to the deployment S3 bucket via a Lambda function. So the Lambda function can provide more checks than just, somebody dropped an artifact in our bucket. It can say, this artifact definitely came from our CI system. It can do a bunch of things that will make sure that your bucket, if there's some kind of compromise, doesn't get polluted with a bunch of firmware or builds that you're not going to deploy to your fleet. What are some of the maintenance red flags we see? Publish permissions being too broad. Devices should not be able to publish anywhere. There are control topics that you should have that are only allowed to be used by trusted sources. Subscription permissions too broad. Devices shouldn't be able to subscribe to any kind of data through the broker. They should have to only get access to the data that they need. You're likely going to have some topics that are sending sensitive data back and forth, whether it's temporary credentials to access services. If all of your devices can get to that, even if you've taken all of these other steps, if they can just listen and get credentials that have anybody's access, then that's going to be a problem for you. Devices controlled directly by other devices. This is the point I mentioned before about control only from the cloud or only from Greengrass or only from some kind of gateway service. That anytime a credential is leaked by accident and you've got access to a device that can control other devices, it can directly impact those devices. And sometimes your options for recourse are very limited. So always try to have some kind of intermediary in the middle there. And the last one that we see, policies not being shared. There are a lot of features in the AWS IoT policies now that let you use policy variables. You can create a shared policy that says how all of your devices should act. If you're creating a unique policy for every single device in the field, anytime you've found out, I need to change this, you're going to have to go back and update all of those. And you're constantly going to have to make sure that not only you've updated all the ones that are there, but any other process that creates those policies has updated them and they're in sync, which can take a significant amount of effort. Now, this all sounds great, but I presume that you've got devices out in the field already, so let's have a quick reality check. Not everything is quite as simple as we think initially. You have brownfield deployments, and in brownfield deployments, you're going to see often one or all of these things. Shared device keys. Somebody started developing the application, they put a key on it, they committed it to the code, and now somebody didn't say, oh, by the way, we're going to need to change all these keys and make them unique and use a secure element in the field. Somebody just said, okay, we're going to ship it. And they shipped out with shared device keys. So now every device has the same identity. Unsigned firmware. This is a big problem because if somebody can take apart your device, whether it's in a private facility or whether it's in end user's location, if they can just put any code they want on it, it doesn't matter if your credentials are locked away, they can just make your device do whatever they want, which is a big problem. Some Brownfield devices don't even have an OTA mechanism, so that significantly complicates things. You may be able to update some files, some configuration parameters, but maybe not the whole firmware. So that can be a big problem for users. And again, I won't harp on this, but enable debug ports, this happens all the time, and sometimes they're impossible to turn off. So you have to come up with some kind of other strategy to deal with that. So how do we deal with this generally? There's really no one-size-fits-all approach. If somebody comes to us and says, I have no OTA and I can't rotate my keys and I have enabled debug ports, is there anything I can do? There's no simple answer for that. What we would recommend first, though, is splitting everything into a separate account. Have your Brownfield deployment data going into a separate account, and then, again, use cross-account roles as kind of a circuit breaker. If something goes wrong and you realize that your Brownfield deployment is compromised, and you want to then make sure that your new deployment that has all these cool security features is not affected, you can just separate the two deployments and make sure that it doesn't affect your new deployment. And then rotate certificates if possible. When you've got a hardware secure element, you don't need to rotate your private keys, but if you've got a device that has unprotected flash where somebody can get to the certificate information and you don't rotate the certificates, as soon as somebody gets that information out, they can just impersonate the device whenever they want. So rotate certificates. If somebody steals a credential, at least limit the window of time that they have to use that credential in your system. So just in summary, go through good, better, best. As I said, rotate private keys, again, only if you have the kind of device that doesn't have a secure element. If you've got a microcontroller that has these things sitting on unprotected flash, you want to take the first step of rotating those keys so that if they get stolen, they're usable for a minimum amount of time. Disable your debug interfaces. As I've said many times before, those debug interfaces, they provide a route into your system, and they also provide sometimes fault injection. You just see strange things happen because those debug interfaces are receiving bad data from somewhere. So you want to make sure that those are always turned off and locked so that they can't be turned on. But the best thing you can do is avoid having your private keys in main memory. There are a lot of ways to do this, trusted execution environments, but secure elements is what we're talking about today. And Microchip has a secure element solution that we would like to talk about. So Xavier is going to tell you how the Microchip solution enables AWS customers to avoid having their private keys in main memory and build strong IoT solutions.
Good afternoon, everyone. So I am Xavier Bignale. I'm Product Marketing Manager for Microchip Technology. First of all, who is and what is Microchip? We are a $4 billion company as of today doing semiconductor devices. That's what we do. We have about 13,000 employees and located in Arizona in Chandler. So we are a global company with representations in each continent. Tim has talked a lot about secure elements, so we're going to go right into it and look at what this secure element is made of. So there are a couple of key blocks. The random number generator was mentioned several times, and when it comes down to cryptography, it is the most essential piece in cryptography, meaning security. The better the quality you have in the random number generator, the best your security will be. Another important component is the memory zone, because that's where keys and certificates will be stored, and we'll get to how we protect it. And then you have the hardware-based accelerators. Depending on the objectives of your system, we'll have elliptical curve, SHA, AES-based crypto accelerators. Now, how do we protect all of that? We have an anti-tampering layer that protects against a physical attack, as well as side attack channel protections, right? So it basically is an 8-pin device that talks over I2C or single wires to your main microcontroller. How does the device talk to the microcontroller? We have something called crypto-auth-lib library. It is a library that is used in the microcontroller that has all the low-level commands to talk to the secure elements. It also has a hardware abstraction layer inside the library to allow us to easily develop software on top of that layer. So what does the secure element defend against? That's a lot of physical attacks. We can go on and on. We have a couple of examples here, such as microprobe attacks, timing attacks. We've got emission analysis, and so forth and so forth. What is the secure element value proposition? There are four main concepts that we articulate to our customers. The first one is to isolate private keys from users. It's common knowledge in security that you, me, or family are the most unreliable factor in security. So we want to isolate manipulations of keys and certificates from us, from the users of the system. The second concept is to isolate keys from software in itself. Software is software. It grows, it's expanded, and it has bugs that are being fixed by patches. So one of the examples where you guys on the IT industry fights hacking is to push patches every hours, half days, or once, every hours or half days or whatnot. There's a general rule of thumb that says it takes about 3 days to an attacker to get into a system, come back, and after leaving or leaving a spyware or malware, or stolen the property that he was targeting. So by fighting that by the hour, it empowers you to mitigate that issue. On the IoT hardware side, how long is it going to take to push such a patch from us, the manufacturer, to our customers, to the end customers, to ripple down to the users inside our houses? It's not going to be an hour, I guarantee you that. So that's one of the first weaknesses. The other thing that's happening in that case, once a company releases a patch, he obviously says what the patch is fixing. So if you've openly said to the attacker where the weakness is, if that weakness is affecting certificates and private keys, now we have a bigger problem. So isolate private keys from software. The third concept is to isolate manipulations of credentials during the manufacturing phase. With the phenomenon of globalization we are going through, contract manufacturers are often overseas, and you have two factors. You have the equipment in the factories, and you have the operators, again, that human factor. So we need to remove exposure of those credentials, the private keys, from those attributes. And the last point is to isolate keys from the microcontroller. Like Tim said, don't put the private keys in the flash of the memory. We've seen an attack. I read about an attack last week where it's usually for, I think it's about a couple of $100. You would be able to send your IoT hardware to a company overseas that would give you the X file. And if the X file contains the private key, you have your firmware completely exposed, your intellectual property completely exposed. And then we can talk about firmware authentication and all the type of features. But then what's happening, once you have control of that firmware, what the person did, they put a spyware, I think it was a thermostat or smoke detector, and then you place it back on eBay, and then you and I are going to buy that thermostat with a spyware on it without even knowing it. And we don't even know the scale of the attack the spyware can generate. That's real world. We are here today. So how do we mitigate all this? We recommend a customer to create a chain of trust. How does that work, and how Microchip, a hardware company, is addressing the problem with a company like AWS? So the first step is for the customer, you, to start generating, from a root of trust, and OEM certificates. Then you open up the AWS account. Then our next step is to go through a secret exchange process where you, the customer, would agree to give Microchip the authority to generate certificates on your behalf. And that's the only interface that there is during the certificate manipulation process. There is no third party involved there. Then what Amazon started to appear, Amazon has a function that's called use your own certificate, where they would take the signer certificates, which have been generated by Microchip inside Microchip facilities, into the user's accounts. In the next step, Microchip generates a fourth level of certificate, which are the device level certificates. That's what's being injected in the factory into the secure elements. Then the secure element generates the private key using the random generator and then ships the device. Well, how do we close that chain of trust? Once the device is assembled in that, let's say, thermostat, for the sake of the example, on the first TLS connection, there's a function called just-in-time registration that would come into the hardware and pull the device certificate into that same accounts. Now we have the signer, the device certificate in the same accounts, and the signer will validate that the device certificate is genuine, and now we've just closed the whole chain of trust without intervention of users, software, or third party. And that will provide the complete isolation of credential manipulation with that solution. And at the end, of course, because every device becomes unique, every single device it has its own customized part number, because you want to be able to track every single IoT hardware that you're manufacturing. And all the handling between the generation of the signer certificates and the device certificate, as well as the generation of the private key, all of it happen inside Microchip secure facilities. So how does manufacturing look like when we develop such devices? The general process is we design. It's probably very similar to what you're going through already. We design, we start manufacturing wafers and assemble dies into the packages. We test that, qualify it, and then ship it. How do we secure that process? Where is the secret sauce? So first thing on the design side of it. There's a couple of key important features here where the most visible and understood one is having an active shield on top of the die that would protect any physical access onto the die. Can't go through the whole list, but everybody has their own favorite features. If you talk to architects, he will swear by the quality of the random generator. One of the features that I think is really appealing is the fact that you have no debug probe points or no test pod. How do we do that? That's our secret sauce. That ties, all of those points ties to the comments the team was making on gaining physical access in some shape or form to the device itself that protects the private key. So during manufacturing, what is the process looking like between you, the customer, and Microchip? So we have our two sides. The IoT hardware is, again, that thermostat, smoke detector, or the lamp, whatever the end customer manufacturer. On the other side, we have Microchip that supplies the semiconductor. So first, you have a hardware project, and you start ordering devices from Microchip. That triggers an ordering system, and with that ordering system, that's where we start to create customized part number. Now you have a unique part number that would be shipped to you. Then we go into that secret exchange phase between you, the customer, and Microchip, and that's where the process starts to be connected to our secure factories. What do we have in those secure factories, and why are they secure? We use HSMs, hardware secure modules. So all those signer certificate, device certificates are being pushed through an isolated network of HSM that are already installed into Microchip factories. The next step is we ship the devices to the production plants of the customers. Here, the important thing is there is no third-party exposure to the certificate and private key manipulation. That is the essential piece of it. So that trust is more than just a technical trust. It becomes a business trust between you and the people around you, your contract manufacturer and your semiconductor manufacturer. How does an HSM looks like? So that's what we actually have in our factories. We have different aspects where the factories are actually monitored 24/7 with video surveillance and guards. There are process of audits that we are subject to make sure we are compliant to given policies and regulations. And at the end, the private keys are generated entirely inside the secure element, inside the facility. And nowhere in the manufacturing process they will be exposed, and nowhere once the thermostat, again, for the example, is in the house of the person, the keys are going to be exposed. You will never be able to extract them at any point of time. So, what are the new features? Last Monday, actually, we released our new secure element, the ATECC608A. We upgraded the random generator. Like I said, it is the source of quality security. Then, Tim hinted a little bit on it. You know, how do you validate your firmware? You have to sign it. Okay, that's fine when you sign it, but then how do you verify the signature is genuine? So we have secure boot capabilities, and the idea is to place the public key that corresponds to the private key this time. And that public key lives inside the secure element. So you want, again, to isolate the entity that will verify the authenticity of your firmware. Okay? So there are special commands within that cryptoauth library that allows you to do that verify function. The next function is the AES acceleration, to be able to encrypt the packets that are going over the communication lines. The fourth new main features, there's quite a bit of them, it's the KDF, the key derivation function, some entity. So from a master key, you are able to generate inside the device secondary keys that are dependent from that master key. Another important, I went a little bit too fast, another important, that KDF function will be necessary for TLS 1.3. So we're already preparing for the next generation of TLS. And then one of the questions we had, that's actually an important feature here too, is how about if I move my secure element from one existing system that's genuine to a counterfeited microcontroller? Well, this function addresses that. It pairs uniquely the microcontroller and the secure element one by one. So you have no way to change the secure element to a new system and try to fake the communication that way. And that concludes all the main set of features into our new generation of secure elements that we use and demonstrate to connect to the AWS IoT service. On that, I will give the presentation back to Tim, and he will conclude.
Okay, so we heard a lot about IoT security and all the features that you can possibly use on these different new chips, all the security steps that you should take. So what's next? Not every company out there is an IoT security company or a security company in general. Most companies want to build a product and they want to release the product, and they don't necessarily want to take on the burden of becoming IoT security experts. So major advice, don't go it alone. If you're using hardware from an existing manufacturer, you need to ask them, what are the best practices? What are the features on the hardware already that I have? What's the migration path from the existing hardware that I have to another piece of hardware that you have that maybe runs identical code but has additional features built on top of it? Write protection, read protection, secure boot, secure flash. There's a ton of them. But you need to ask them not only what features are there, but how you should use them. Because using one feature on its own usually doesn't do it. You need to have a combination of all these features together, implemented properly. Otherwise, you don't end up with the security that you think that you have. So go to Microchip or whoever your provider is and ask them what their best practices are.